All right, so today we're going to be talking about Avogadro's law. Right now, how did Avogadro's law come to be? Now, a lot of you might have seen the equation in this format before, but the original equation came from comparing the volume to the number of particles, or the moles. That's what N stands for, the number of moles, which gives us the amount of particles. Now, what Avogadro's law says is the more particles, the bigger the volume. The less particles, the smaller the volume. And kind of thinking about it, I don't think it really takes a genius to figure that one out. Like, if you have a balloon and you blow more air into it, it's going to have more particles. But that kind of seems no duh for us now. Back in the day, there's some groundbreaking stuff, all right? But when the volume of a gas was compared to the number of the particles, it always came up to some value. Let's call that value A, right? Now, if the gas was at a different volume, we'll call that volume 2, then it had more particles. It had a different amount of particles, but it was bigger, right? If V2 is bigger, then the number of particles must also be bigger. But if you have that ratio, it still gives you the value A. And if you go even bigger, it will always give you this value, this constant, right? And this is called a proportionality constant. And what it does, well, if you know that V1 when compared to N1 gives you A, and V2 compared with the new number of moles also gives you A, you can set these two equations equal to each other. You can set this equation equal to this, and you will get the Avogadro's law that you know and that you love. All right, and I'm going to show you how to use this equation, and then in the upcoming video, I'm going to show you how all of these gas laws together combine to form the ideal gas law and the combined gas law. All right, so keep that in mind. Now, this equation right here, this zero, you usually call it a knot. I don't think we've talked about this notation before, but it just refers to your initial reading, right? Usually at time 0, or just the very first piece of data that you get. It comes from the English word for nothing, meaning not. I don't know, but, or it's called not, it means nothing. All right, but let's do some actual practice problems right now. Keep in mind that this equation is when, well, this equation holds true when pressure is constant and temperature is constant. All right, so pressure and temperature must stay the same in order for this relationship to work. All right, so let's take a look at it. So suppose we have 12.2 liter sample containing 0.50 moles of oxygen gas. All right, so we have, let's see, 12.2 liters of oxygen gas. All right, whoops. And then we have 0.50 moles of O2. The pressure of 1 atm and a temperature 25 degrees Celsius. Now this right here might scare you off a bit, because you might start to try to think of other questions to solve for, but if you continue reading the problem, it'll let you know that you don't really need this information. It says, if all of this O2 were converted to ozone at the same temperature and pressure, what would be the volume of the ozone? So the fact that they said the same temperature and pressure means that this number isn't going to change, so this is irrelevant to us. It's just there to throw you off or to give unnecessary detail. But what we're looking for is the volume, so we're looking for the liters of ozone. We're looking for the liters of ozone. Well, how do we get the liters of ozone if we don't even have the moles of ozone? Sad. They gave us all this information, but we still have two variables that we're missing. I just realized my face is up here and you can't see this equation. But I'm going to write this equation here. Now, whenever you're dealing with Avogadro's law, you need to think of some stoichiometry. You got to think of the mole ratio. All right? The comparison of two species in a chemical reaction. So O2, we need a balanced chemical equation. So we got to make these numbers the same. So this 2 and these 3, which have the same number of particles on each side. So how do we do that? We put a 3 here and we put a 2 there. 2 times 3 is 6. 3 times 2 is 6. Same number of oxygen atoms. We have a balanced equation. So how do we use this? Well, we know that we have 0.5 moles of O2. That information should give us the amount of ozone. Sorry, this should say moles of ozone right here. That's a little ugly. I'll fix that because some of you are going to complain. There we go. So let's turn these moles of oxygen into moles of ozone. And then we'll use our equation. Come back here. There we go. All right. So if we got 0.50 moles of O2, and we want to turn that into moles of ozone, so we want moles of ozone, but we have moles of O2, we got to use the mole ratio. So in front of the oxygen, there's a 3. So we're going to put 3 moles of O2 here, and in front of the ozone, there's a 2. So there we have it. Now, 0.5 times 2, that's 1. 1 divided by 3 is 0.33. And this is moles of O3. Take a look at our units. The moles of O2, they cancel. Only thing left, moles of O3. So now we have the moles of ozone. We have them. We have them here. Now what we need to do is find the volume. And what we're going to use this equation here, we're going to use Avogadro's law to solve for it. So let's go plug our values in. So we got 12.2 liters right here at the top, and then the moles of oxygen at the bottom. All right, and then this is equal to the volume, which we don't know. We'll just call it V. We'll call that V2. Or you can be more specific. You can say V of O3, the volume of ozone. All right. And then underneath, you can put the moles of ozone, 0.33 moles of O3. So how do we get this, the volume of ozone? Well, we gotta get it by itself. So let's get rid of this number at the bottom. Right now it's being divided, so let's do the opposite and let's multiply to both sides, because you got to multiply to both sides so they don't get jealous. All right, so I know it's a little ugly, so don't hurt my feelings. All right, now volume of O3 is equal to, and let's just multiply this stuff out. All right, so quick mental math. 12.2 times 0.33 divided by 0.5, and we get 8.05. But we only want 2 sig figs because look, the limiting data that we have is 2 sig figs here, 2 sig figs, so we should only have 2. So 8.05, we're going to round that up to 8.1, and the units for volume were liters, so we're going to leave that right there. And that's how many liters we have of ozone. All right, so there you have it, Avogadro's law. If you want to keep watching, I'm doing another example, but if not, have a good day. All right, let's take a look. This is an example in the book, by the way. This This is on page 172. So if you want to go back and look through it, feel free to. But let's check out a very similar problem, but this time it's containing nitrogen gas and ammonia. And look at that. I balanced the equation for you. I'm so nice. Given 5.60 liters of 0.88 moles. Okay, so let's do that really quick. We have 5.60 liters, 0.88 moles of, oh, that L looks a little weird, moles of N2. They give us a pressure of 0.75 and a temperature, but then again, they tell us the same temperature and pressure, that things stay constant, that those numbers are irrelevant. But we don't know either one of these. So let's find the moles first because we have our balanced chemical equation. So 0.88 moles of N2, well, we want to turn that into moles of NH3. So moles of NH3 are going to go on the top because that's what we want to figure out. And then we are trying to get rid of our moles of N2, so that's going at the bottom. Now the numbers right here are going to come from our balanced chemical equation. We have 2 NH3s for every 1 N2. So it is a 2-to-1 ratio. So 0.88 times 2. What is it? I don't feel like doing math. We get 1.76. You guys should get good at doing that in your head, okay? But we're not going to round to the very end. I know there's 2 sig figs here. Do not round to the very end, because if you round here, then you're going to use that incorrect number here. You round at the very, very end. All right? So moles of NH3. Look at that. We have the correct number of moles. So 1.76 moles of NH3. Now, let's use Avogadro's law. Let's bring this down over here. And let's plug things in, and that's basically it. Plugging things in, that's all you're doing here. 5.0. You guys can hear some stuff, I'm sorry. 0.88 moles of N2, and then this is equal to our second volume, and we have our 1.76 moles right here, moles of NH3. So what we got to do is get rid of this denominator, right? So multiply both sides by 1.76 moles of NH3 to both sides. Whatever you do to one side, you got to do to the other. It's the rules of math, all right? If you're going to use math, you got to follow the rules. So it cancels here. Boom and boom. So we know that, whoa, that our volume, our V2, is going to equal all this junk on the left. So 1.76 times 5.60 divided by 0.88, and we get 11.2. But since we only had 2 sig figs here, we're only going to use 2 sig figs. So we're going to have 11 liters as our answer. All right, and that right there is it, people. So that is how you use Avogadro's law. And then yeah, that's it. You could also use it like this. Either way would be fine. I don't know, you end up getting the same thing. It doesn't matter. All right, so have a good day, people.